talking about the notion of the limit, right? So can anyone does anyone remember what the limit, what it means for a function to have a limit? So if we say limit of f of x is L as x equals to c, right? So limit of f of x is L as x equals to c. What does that mean? What does that mean? Kylie. Okay, so as the inputs get closer to C, the outputs get closer to L, right? Can somebody give me like the more modern version of that? Edie.
If f is a real function and c is a real number, and as x approaches, let's see, absolute value of f of x minus L is less than or equal to any number epsilon that you might choose. So that, let's see, so that x minus, let's see, something is less than delta. How's that go? Let's see, c minus x minus c is less than delta. For the absolute value to be greater than 0. And less than, let's see.
Hard to do, right? Can anyone? So the pieces are coming out. Can anyone put the pieces together in the right with the right relation, or like sort of explain? Can anyone do make this a little bit more precise? Alfred.
Well, I kind of remember something like as x approaches the left side of C, and x approaches the right side of C, but I'm not sure where that would fit in.
Okay. So that's something we haven't talked too much about, the left and right limits. But I'd like somebody to talk about epsilons and deltas. What does it mean, right? What does it mean that the limit is L as x approaches C? The limit of f of x is L as x approaches C. What does that mean, Joey?
Given any tolerance epsilon, where f of x minus L is less than epsilon,
For f of x minus L,
to be less than epsilon.
do you say to be less than to be less than epsilon?
Which one comes first? I'm not sure, the chicken or the egg, but therefore x minus c, absolute value of x minus c, it will give x minus c, that number will be less than delta but greater than 0.
Now we're running into problems of English language, right? So like for this to be less than epsilon, therefore, right? Problems of, so you see that even in English, this grammatical, right? So can anyone put it in the right? Can anyone say this? Actually, maybe I should stop bullying you guys. Yeah, Cynthia, please.
Well, like, I don't really know how to use it, but given any tolerance, you can find a distance.
Yeah. Given any tolerance, one can find a distance. So this is the tolerance. This is the distance, right? So that what happens? Amaya.
I think if the delta is greater than 0, like the distance of x to c is less than delta but greater than 0, and the distance of f of x from L is less than epsilon.
Almost. So here's the trouble with it's almost right, except for the word and, right? So you say if this and this, right? right? So again, sort of grammatically, there's something like there if it's if this and this, there should be something that follows this, right? Like then something happens, rather, right? So
We'll just change and to that.
and let's change and to that. And to that. That's so this is the definition. Okay, this is the idea, right? Given any tolerance around epsilon, one can find a distance delta, right? So somebody gives you no matter what pair of bars you're given, centered around L. There's a distance to C. There's a distance to C that we call delta. So there's a interval centered around C, in which all the outputs lie within those bars. There's a distance. We can find a place. We can find a place around C where those bars are satisfied. Okay. So really, you can think of this in terms of intervals. Okay. Given any interval centered around L, there's an interval centered around C where all the values lie in that interval around L. Given any interval around L, there's an interval around C in which all outputs lie in L minus epsilon, L plus epsilon. Right? Except maybe at C itself. Okay. So so this is the idea. I'd like to say one thing. The very first thing that Edie said was this: that f of x minus L could be made smaller than epsilon for all epsilon. Right? F of x minus L could be made smaller than epsilon for all epsilon. Right? It's not exact. That's not exactly right. If you could do this, suppose you had that these two numbers are smaller than epsilon for every epsilon. What would that tell you about these two numbers? Right? These two numbers are smaller than any tiny number.
So you choose a different epsilon.
It must be essentially the same.
They would be the same number. This would mean that f of x actually equaled L. This would mean that if you said something like this, then that would actually imply that they're the same number, right? Because if you have two numbers and their difference is smaller than anything you choose, then that forces them to be exactly the same number. Okay, so the order of the phrasing is actually really, really key. I won't go too much into it. Okay, so I think now you're starting to be in the right mood. Okay, so we're gonna talk about one of the statements that we gave last time, and we're gonna do it in detail. Okay, so just to show you how the limit definition works. Okay. So which one should we do? Let's do this one. Okay. So uniqueness. So we stated this way last time. Suppose that the limit of f of x as x equal to c is L, and suppose that the limit of f of x as x equal to c is M. So you go into a room and you come out saying, "Oh, the limit is L." Your friend comes out saying, "Oh, the limit is M." Okay. Then those must be the same thing. Okay. In other words, there's only one limit. You can have only one limit. Okay. So we'd like to, that's something that you hope happens. Let's see how it happens. Okay. Why are we guaranteed this? I don't know if you think this is interesting. I hope you think this is interesting. I don't know. But even if you don't, I'm going to show it to you. Okay. So here's what you say. We say, well, look, here is L and here is N. Same. And we're going to show that the distance between these guys is smaller than any number. Okay, here's our strategy. We're going to show that if each of these guys is a limit, well then the distance between them, so strategy, if both are limits of f as x equals to c, then the distance between them is smaller than every number. Okay. The distance between them is smaller than epsilon for every epsilon bigger than 0. Okay. And that will tell us that they must be the same number. Okay. Just like we commented a few seconds ago. Okay. So here's the idea. We say, well, look, here is C, right? Here is C, so the first thing I'm going to do is show that these guys are within 1 of each other. Okay, and you'll see that we can do that for any number. Okay, so here's C, and I know that if I take L plus a half and L minus a half, then there's a place around here where everybody lies within half of L, right? So take epsilon to be a half. Then there's an interval c minus delta 1, c minus delta 2, in which f of x minus L is less than a half. Right. I know that everybody in here lies in the half interval around L. Okay? Right. If I take any guy here, it's going to lie between the bars. Everyone all right? Any questions? Feel free to stop. I know this is a little bit weird. Yes.
Just in the notation, what's
Yes.
that upside down A?
For all. Okay. Other questions? You should feel very free to ask at this point because this should be very alien to you. Okay. Okay. Now, further, there's an interval c minus delta 2, c plus delta 2, in which, what am I going to say? In which what happens? Does anyone see what I'm going to say? Can anyone guess what I'm going to say? Joey.
In which the absolute value of x minus n.
Yeah, great. There's going to be a place where, well, everybody in that interval lies within a half of m, right? All their outputs lie within a half of m. Right? So there's some interval delta 1, right, plus delta 1 minus delta 1. There's also some interval plus delta 2 minus delta 2, in which everybody lies within a half of m plus a half minus m. Okay. Does anyone see the punchline? Does anyone see the punchline? Emily.
Well, the deltas be delta 1 be the same as delta
No, they need not be the same, but you can certainly take the smaller of them. You can take so if you take the smaller of them, then everybody in the smaller guy, their outputs will be within half of here and within half of M also. Yes, Elizabeth.
Shouldn't the, delta be delta 1?
Ah, yes, thank you.
It could also be plus or not.
Yes, thank you. Sorry. Okay, so here's the punchline. You say, well, look, choose a point in the intersection. Right? Choose a point in the intersection. Right? You've got these two intervals centered around C. Choose a point that lies in the smaller. Right? Choose a point that lies in the smaller interval. Okay. Then what do you see? Choose a point x in the intersection. Then what do we know about that one point? Well, f of x minus L is less than a half, and f of x minus M is less than a half. Right? Because lying in the first interval meant your output's distance to L was less than a half, and lying in the second interval means that your output's distance to M is less than a half. Right? So if you lie in both intervals, well then both of these things are going to be true. Anybody confused?
Mm-hmm.
Yes, okay, great, thank you. Okay, where are you confused, Sharon? Yes. Sharon, I think you. Oh yeah, but I think you nodded your head, Sharon.
Oh, this is Gerald.
General confusion, yeah. Rachel, yeah.
I just don't totally understand. Where's the point that you're like picking, and why does that mean that this works?
Okay. So let's step back. For a second, right? You're told that these two things are limits. Okay. You're told that these two things are limits, right? And so somebody gives you, if L is a limit, well then there's a place where you can get within a half of L, right? M is also a limit. Well, there's some interval in which all the outputs are within a half of M, right? Is everyone okay with that? Right? That's what it means to be a limit, right? L is a limit, so it has this property. M is a limit, also has the same property. Okay. So there's an interval in which everybody is within a half. There's an interval in which everybody is within a half of L. There's another interval in which everybody is within a half of M. Choose somebody who lies in both intervals. Choose an x that lies in both intervals, right? Right? They're both centered around C. You take the intersection. The smaller, if you lie in the smaller one, you lie in both of them, right? Because you lie in the smaller and the bigger, right? Okay. So for that point that lies in both of them, right? Just choose any guy that lies in both of them. Okay. For that guy, the distance of her output to L is smaller than a half, and the distance of his output to M is less than a half. Sorry, I'm used to referring to these things as male for some reason, but I guess that could be female. And I refer to everything as a guy. Like, there's this guy, and then, sorry, maybe I should change that, having been here for almost a decade. Okay. So the distance of the output to L is less than a half. The distance of the output to M is less than a half. What does that tell you about the distance between L and M? The same as what? The distance of me to Ellie is less than half a mile. The distance of me to Michelle is less than half a mile. How far are Ellie and Michelle from each other?
Less than half.
Less than half a mile?
I mean, less than half.
Less than a mile, right? Less than a mile, right? Because the distance between them is going to be smaller than the distance of one to me and me to her. right? It's less than a half plus a half, right? Okay, so what does that tell you? The distance of L to M is less than 1. The distance of L to M is less than 1. Okay, is everyone all right? Everyone okay with each bit? Okay. And the whole thing may seem confusing, but think about it in bits. What does this mean? Okay, so the distance of L to M is less than 1. Now we can do the same thing again, right? This was 0.5, right? You can do this for any number, right? If I took this to be 0.05, what does that tell me? The distance of L to M is less than 0.1. If I took this to be 0.005, that tells me the distance of L to M is less than 0.001. In other words, right? So. Similarly, one sees that the distance of L to M is smaller than epsilon for any epsilon. Okay. And that tells you that they must be the same number. That tells you there could have only been one. Or there can be only one. Nobody got the joke. That's okay. It's a reference. There can be only one. You see how the students have changed with time. I think 10 years ago, if I made this joke, it would have been recognizable. Which is why I've stopped making matrix jokes in my linear algebra class. Okay. Does everybody see that? Okay. So this is how the definition of limit is used to ensure these properties, right? So last time we put up all these properties. There can be only one limit. If you take the sum of limits, it's going to be the limit of the sums, et cetera, like all these properties. It's all this sort of argument. Okay. So let me. Okay, I won't do another example. Okay. So let's go backwards. So remember. Right. The other things we showed that the limit of sum is the sum of the limits, right? As x equal to c, right? Et cetera, right? The limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits, et cetera. And we finish up with this statement that. If p is a polynomial, if p of x is a polynomial, then the limit of p of x is just p as x approaches c, is just p evaluated at c. Right? You remember that's basically where we stopped. Right? That if somebody gave you a polynomial and said, what's the limit as x approaches 5 of this polynomial? All you need to do is plug in the value, right? You need to say it's going to be 100. Right? That's where we stopped, and this was because of the previous. This was a consequence of the previous set of statements. It's also true, so that's actually part one. If p and q are polynomials, then again the limit of the quotient of these guys is again going to be just the thing evaluated as long as c is non-zero. I'm sorry, as long as QC is non-zero. me just read it for now, and then I'll try to remember from here on in. If p and q are polynomials, then the limit as x approaches c of p of x over q of x is p of c over q of c, as long as q of c is not equal to 0. So what's the point? The point is that, remember we said that you can't just evaluate the function to figure out the limit, right? We said that, for general functions, you can't just say, oh, I'm going to take the value of the function there, right? Because the function could skip. The function could skip, and if I evaluate the function there, I might not get the limit. Okay, but what this is saying is that for polynomials and rational functions, it's okay to do that. That these functions actually don't skip. Okay, these functions don't skip, and so it's all right to evaluate them at the point to figure out what the limit is. Right. In other words, that their behavior is sort of predictable. Right. As you come in here, it starts tending towards some number. It's going to be that number. The value there is going to be that number. It's not going to jump. Okay. Okay. Any questions? Any questions? One of my a friend of mine at Pomona, a math professor at Pomona, asks her students to ask her one irrelevant question every day. So like she'll say like, any questions? And then they'll ask her something completely random. But I don't think I can handle that. Yeah, to me that's just a recipe for disaster. Yeah. Okay, so last thing in this section, something very important, something called the squeeze theorem or the pinching theorem, aka the squeeze theorem. Okay, so here it is. Okay, so suppose you have three functions. Say you have three functions, f, g, and h, right? Are all functions. Are all real value functions, right? And you know that in some interval c minus delta, c plus delta, one has, let's say, f is smaller than g, which is smaller than h. Okay, so you have these three functions. If we're looking at their graphs, right, so there's some c minus delta, c plus delta, or like this, c minus delta, c plus delta. So there's some interval around c, and in that interval, f is always lower than g, which is always lower than h. Okay, there's some hierarchy between them in that interval. Okay, so you have three functions and there's a hierarchy between them. Okay, if the lower guy tends to some number and the upper guy tends to that same number, then what? Then what? Ellie?
The middle function is going to tend to the same number.
Great. Who is speaking?
No.
Yeah, it wasn't you, Ellie. Who said the middle one before I called on Ellie? Somebody over there. Ah, okay, great. Shravya? No, it's Shravya. Great. Yeah, then the middle one, then the limit of the middle one is going to be L also. The limit of the middle one is going to be L also. Okay. So maybe that sort of intuitively makes sense, right? If you have, there's some L, and here is C, and you have one function, and it tends to L, and you have another function, and it also tends to L, right? So you have H here, and you have F here, and you have another function, and it's going crazy, but it's trapped between these two functions. Well, no matter how crazy it is, because it's trapped between those two, it will also go to L. Okay. So G is the crazy one. Okay, so let me show you how to use it. For example, let's say like this. So let g of x be, say, x sine 1 over x. X sine 1 over x. Okay, right? And what's the limit as x equals to 0 of g of x? Okay, so I'd like you to think about this for a second, right? This is a limit, this is a product, right? It's one function times another function. So you might think, well, I'm just going to take the limit of the first guy times the limit of the second guy. Because I know that if both of them have limits, then I can just take the product of the limits. Right? What's the limit of x as x goes to 0? 0. What's the limit of sine of 1 over x as x goes to 0? Right, exactly. That's the right answer. That's the right answer. There actually is no limit. There actually is no limit. Sine 1 over x as x goes to 0 will look like this. Something like that. Okay. So as it gets closer to 0, this 1 over x heads off to infinity. And sine of 1 over x oscillates, as that 1 over x goes off to infinity. Okay. So it has no limit. Okay. But the good thing is that it's multiplied by x, and so that means that so this is the graph of sine of 1 over x. But if you multiply it by x, actually it's a lot more manageable. And you can see that by noticing that one uses the squeeze theorem. You say, well, look, I know that this thing is smaller than the absolute value of x. Right? And the reason is, I know that this thing, well, I should maybe break it up further. I know that this thing is smaller than its absolute value, right? Whenever you take the absolute value of something, it gets bigger, right? Okay, and this thing is the absolute value of x times the absolute value of sine of 1 over x. Right? Because the absolute value of a product is the product of the absolute values. Right? That's how the absolute value works. Too low. Too low? Too low. Right, so I know that this thing is smaller than its absolute value. I know that this thing, the absolute value of a product equals the product of the absolute values. Right? And what do I know about the absolute value of sine? Smaller than what? 1. Smaller than 1. Right? So this product is smaller than x times absolute value of x times 1. Right? Because this value of the sine is trapped between the absolute value of the sine is between 0 and 1. Okay. Okay. And similar argument gives you the opposite sign. One can also see that this thing is bounded below by negative absolute value. That is, the crazy function in the middle is beneath the absolute value function and above negative the absolute value function. Right? It's trapped in these regions here. Rachel?
Sorry, I'm confused
Mhm.
about where you're getting the absolute value, how you're saying this.
This part? This thing here?
Yeah, where are you getting
Okay, it's right. How about up here? Is it okay? This thing is smaller than its absolute value. This thing equals the product of absolute values. Right? Because the absolute value of A times B is the absolute value of A times the absolute value of B. Okay. So this thing is smaller than this product here, and I know that the absolute value of the absolute value of the sign is smaller than 1. So I'm going to replace this thing by 1. Replace it by 1. Okay.
replace x with that?
I replace this thing by 1, by something bigger, right? I'm going to multiply this thing by something bigger and say, well, this thing is smaller than that, right? Because I replaced the second factor by something larger. Okay, so that's good, right? We see that the function, which seems sort of intractable, is actually trapped between these two guys, and we know that the limit of the left-hand guy as x approaches 0 is what? 0, right? And the limit of the right-hand, right? The limit of the upper guy is also 0 as x approaches 0, right? So, our function, crazy-looking function, but it's trapped between these things no matter how crazy it is, and so its limit is also 0. Right? So the limit of the guy in the middle, sine 1 over x, is also 0. So it's approaches 0.
But isn't when a graph is like oscillating, doesn't that mean it has a limit?
Not necessarily, right? Because here, even though it's oscillating, its values are getting. I can make this thing as close to 0 as I want, right? For the limit to be 0, think what that means. What does that mean? That means that can I find an interval in which this thing is within 1 of 0? Sure. Can I find an interval in which the crazy guy is within 0.1 of 0? Sure. Can I find an interval in which it's within 0.001 of 0? Sure. Right? And that's because its behavior is controlled by these column guys. Okay. So yeah. So even though it is oscillating, but its oscillation is controlled. Okay. 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 So let's see. There are a couple of consequences. There are a couple of important consequences of this fact. So consequences of the pinching thing. So I'm just going to list them for right now. So the first is this, that it's called Theorem 3 in the book. The limit of x to the 1 over n as x approaches c is c to the 1 over n, where n is some natural number, and c is some real number. So if you take a root function, then you're taking the limit of a root function, you can just evaluate it. Okay. Second, Theorem 7, the limit of sine of x as x approaches c is sine of c. The limit of cosine of x as x approaches c is cosine of c. So again, sine and cosine are functions which you can just evaluate. If you want their limits, you can just evaluate. And this is a consequence. These are all consequences of the pinching theorem. Theorem number 5. If the limit of f is non-zero as x approaches c, and the limit of g is 0 as x approaches c, then the limit of f over g doesn't exist. The limit of the quotient doesn't exist.
What are different numbers when you do
Sorry?
that? No, like theorem 3 is that theorem 7 and then theorem 5.
Yes, I'm afraid that's true. Yes, 3, 7, and the 5. These are from your text. These are the numbers from your book. So if the guy on top goes to some non-zero number, and the guy on bottom goes to 0, then the limit doesn't exist. That's sort of what you would expect, right? If the bottom goes to 0, the top doesn't go to 0, then the quotient is not going to exist anymore. Yes, Sarah?
Is that does not equal 0 for the theorem side and first one?
I'm sorry, say it louder.
For limit of f of x, is that does not equal 0 for that?
Does not equal 0, yeah. If the top guy doesn't go to 0 and the bottom guy does go to 0, then the quotient is not going to exist. The limit of the quotient won't exist. Emily?
For number theorem 7, I understand like why those are true, but why is that a consequence of the squeeze theorem? What are the two things actually?
Yeah. I'd like to say it, but I don't have, maybe I don't have the time to say it. Yeah. So let me show you, instead of talking about those guys, I want to talk about something more important, which is this limit. It's a very important limit, sort of a famous one. The limit of sine x over x equals 1 as x approaches 0. Okay. Right. What's the limit of x as sine goes to 0? Well, it's 0. Right. What's the limit of sine x as x goes to 0? It's also 0. Right. So if you evaluate these things independently and say, oh, I get 0 over 0. Right. It turns out that these things approach 0 at the same speed. They go to 0, but they go to 0 at the same speed, and so the limit is 1. Okay. And let's see how this works. Okay. So why? Okay. So if we look at the unit interval, the unit circle, and we take some angle x, okay, then I'm not going to ask you, I'm just going to tell you, right? Right? You know the height of this, right? What's the height? What's the width? Sine is the height, cosine is the width, right? So the area of this triangle is 1/2 height times base. Right? That's the area of that triangle. Okay? What's the area of this circular sector here? What's the area of this sector here? So pi r squared, and we have how much of it? We have x over 2 pi, right? So pi's cancel out, and we get x over 2. Right? So the area of the sector is x over 2. Right? Okay. Now I'm going to put in another triangle, right? Right. This length here is 1, and the length here is what? Do you know? Can anyone see this quickly? If not, I'm just going to tell you. By similar triangles, right? Because this is sine and this is cosine, right? The ratio, the length here must be sine x over cosine x, right? By similar triangles. Okay. So we know that the area of the big triangle is 1/2 sine x over cosine x. So now I'm going to divide everything by multiply everything by 2. And I'm going to divide everything by sine. So I get cosine x is smaller than x over sine x is smaller than 1 over cosine x. Just one more second. Now, what's the limit of this as x goes to 0? What happens to this thing? Cosine x goes to 1. What about this thing? 1 over cosine x will go to 1 also. What does that tell you? The guy in the middle, x over sine x, must also go to 1 by the squeeze theorem, right? Which tells you that the limit of the opposite guy will also go to 1. Okay. So this is an important result used in physics a lot. Sorry to hold you over time.